Okay, good morning or afternoon, everybody. The objective of the presentation is for the students to understand the need to work engineering within a systemic view, but also a holistic approach in what they do. There will be links to road mobility. I've noticed there has been a few questions, but the focus, of course, is on air mobility, and the bridge is the electrification, of course. So the focus today is on efficiency and CO2 emissions. Here you have a view of what could be a systemic approach with the topic. So that's the topic line. And you also understand the holistic approach with the other lines. For example, the disciplines involved, the role of public policies, the impact on societies, of the choices we can make when designing a propulsive model. Okay, so I will move on. So we know aerospace or air mobility in general is very global, but you will understand that the impacts can be very local. When we look at mobility, and especially at air mobility, we must acknowledge that it means the total decarbonization of the energy sources. This is higher than for cars, because when we look at a plane, in fact, 99%, when we look at the life cycle analysis, 99% of the emissions are linked to the combustion of the kerosene, biomass, and or electricity. And by regulation or the market, I personally would prefer regulation because the side effect for the populations will be huge. We must acknowledge that it will have consequences in our territories because we will take massive amounts of electricity and biomass. On this slide, I try to show that the effect the technology can play, but if we have a rebound effect known as the Jarin's paradox, which is that you can improve a system, but if the use of that system is increased, then the overall effect can be on the wrong directions. And this is the case for air mobility. We have improved the efficiency of planes for the past 60 years, but this came with a lower price of the ticket, and so roughly we divided by 4 the fuel burn per passenger kilometer, but at the same time the traffic was multiplied by 20. So you can see that the fuel burn and the emissions associated just keep rising. Here is a scenario I modelized. I pick basically, I'm not sure you will see the animations, except if I do this, okay. So if the traffic keeps growing of 3% compound annual growth rate per year, which is what's happening today, we keep the efficiency, which means high engineering to keep improving the planes and engines efficiencies. The trend is 0.85% per year. You can see that since the market will grow faster than the engineering efficiency, the fuel burn and the emissions keep rising. So the only way, and even it's not enough, is to go into 100% decarbonization of energy by 2050. I do not believe this will happen, but at least this should be the goal. So when we talk of decarbonization of energy, and this is valid also for electricity, when we look at road transportation, we must make sure that it is sustainable. For example, for electricity, that the electricity is low carbon, which is not the case in many parts of the world, and it's not the case in India, as you know, for now. We also must look at optionalities, which means, in fact, competitions or conflict of use, because when we look at biomass and electricity, you have many players. And there also, we must understand that we come from the oil world, and oil today is massively dedicated to mobility. Okay, so when we shift from oil to other sources, such as biomass and electricity. Biomass and electricity, they did not wait for mobility to be used by populations. So there will be multiple conflict of views, and we must understand that when designing systems. And also we must understand the economics. And the economics, and especially for the biomass, the economics is a collectability. If you have, and you will see that on the map very soon, if you have a dense energy, it could be okay. But if you have very low energy, for example, in lignocellulosic from the trees, this means a very low collectability. This means a very high cost for the societies. This is a map I mentioned. This is something, and you must understand that most of the engineers know what's going on for decades. This is from May 2009, so roughly 15 years ago. This is the impact if we want to have plane flying across America, or United States to be precise. This is the surface of land we need to feed those aircraft flying in United States. So it's not the planes outbound of United States. This is purely domestic use. And you can see that we need, for the 1G, for the first generation biofuels, we need extensive surfaces, palm oil or corn. And if we move into the second generations, so the waste, typically the jatropha or the camelina or other plants which are seen as energetic plants, you can see that basically you need half of the surface of the country just for the domestic planes of that country. So this is not in sight. I mean, we cannot achieve that. Algae could be, but algae has many, issues. And especially, in fact, you need more energy to extract the oil from the water than you can get of energy from that oil. So algae, it's good in I would say for R&D, but it will not come for decades, that's for sure. Understanding also what means for the society, so in a holistic point of view, the decarbonization of energy. This is a work I've done 3 years ago with the French Academy of Technology. This is what we want to reach for France in a decarbonization way. So each line is basically what we need to reach by 2050, 2045, 2040, just based on the regulations. So for example, in 2050, we need 6 million tons of sustainable aviation fuel in France, which is approximately 70% of the projected needs. And what it shows is that here we have the maximum output of bioenergy in France. Roughly, we will need to collect 6 million tons of bioenergy coming from the biomass. I mean, this is the maximum we can get from France. And if we want more, that means we need to import. But for the biomass, importing is very, very costly, so it will not happen. And the other countries also will need the biomass. So since we have a maximum of 6 million tons available, and it's not enough for the need, we will need to put electricity as well. And so what it shows is that in a scenario of, for example, 4 million tons, what we need to reach in 20 years, if we have 6 million tons of biomass available, it means we will need roughly 100 terawatt hours of electricity just to meet roughly half of the need, because today we use 8 million tons of kerosene in France. So what does it mean? It means that 20% of the country's electricity production plus 100% of the biomass available for bioenergy needs to be directed to air mobility. Air mobility is approximately 10% of global mobility. So I will always defend that road transportation needs to go to the most efficient pathway. And you will understand in a few slides that I consider that the most efficient pathway is full electrification. Basically, it comes with collateral damages. No energy has no collateral damages, but we need to look at efficiency and then also at equity, because when you take 100% of the biomass and 20% of the electricity, you can imagine this will have side effects for the populations. among the side effects for the population is the price on commodities. Here you have a study from the US Academy of Science in United States. They worked for approximately 15 years over the period. And what they demonstrated is that the price of commodities such as corn, soybeans, or wheat is affected by the policies on biofuels for transportation. And the effect is already very huge. I mean, biofuel for transportation is less than 5% of the fuel, but still you can see the effect on commodities such as corn is 31% increase of price for the corn, or 20% for the wheat, basically. And this is food for the populations. So we must understand that our choices have significant side effects for the entire populations. This is why a holistic view is mandatory when you look at your energetic system. When we look at efficiency, and especially when we come from fuel, from oil, and we look at energy, we must understand energy return on energy invested. This is, I would say, key in every design, because every propulsive system will use primary energy, then transform into an energy carrier. So energy return on energy invested, basically, we come today from here, onshore, offshore oil, mainly. This has very high return on energy invested. Basically, you place one, you get 20 to 70 for onshore. So this is very, very efficient. And then you can lose that efficiencies in an internal combustion engine, which has a 30-40% yield. You can afford that because you have a very, very high energy return on energy invested at the beginning. But where we are going is here. I mean, biofuels and e-fuels based on hydrogen are pure exergy. I mean, we lose, I would say, everything. I hope you have that insight, but my first year students in engineer generally, they tend to forget that. But the lower heating value of hydrogen, which is the core of an e-fuel, basically, the lower heating value of hydrogen is 33 kilograms. So you have 33, I would say, kilowatt hour of energy in 1 kilogram of hydrogen. But to split the water molecule, H2O, to get that hydrogen, you need 50 to 60 kilowatt hour. So you are destroying energy. It's a negative, I would say, energy return on energy invested. And you need to acknowledge that, because this means you need to be very, very clever in all the systems you will design. So sooner or later, we must understand that it's not the technology which is the issue, especially for the sustainable aviation fuel, but it is the availability of the inputs, the very low energy return on energy invested, and the cost associated. And since we are dealing with molecules which are very precious because of the above, you need to be very, very wise. And since I already mentioned it, there are no energy which comes with no collateral damages. Please be very, very clever and be very, very wise. Let's go into cradle-to-grave, and I will translate that into well-to-wake. I will explain in a few. So basically, we go into the life cycle analysis there, and when we translate that in an energy systems, basically we go from the energy carriers and we have the associated propulsive architecture. So this is where we come from, primary energy, which is oil. We get a fuel tank, and then we get an engine. In our case, in aerospace, it is a gas turbine. The system will be very, very similar, in fact, identical, when we go into e-fuel or biofuels. But if we want to deal with full electric, or if we want to deal with hydrogen, then the system will be slightly different, especially for electrics, of course. So from the cradle to grave, here we translate into well to wake, or the well to rotor. And the figures you have here are the same as for road transportation. So I believe that most of you already have those figures in mind. When we go in direct electrification with battery, if I place a base 100, basically I take 100 kilowatt hours of electricity from the grid. Okay, so electricity is an energy carrier, but in that case, I could consider electricity as my primary energy for the system. But of course, it remains an energy carrier. So if I pick 100 kilowatt hour of electricity from the grid, I will lose some of that energy in transport, storage, and distribution, approximately 5%. I will lose some more in the AC-DC conversion. I will lose some more in the battery heat management, for example, and I will lose some in the e-motor during the conversion with the friction. But the global yield still remains very high, 83%. So I have a system with a yield of 83%, which is, in a kind of way, pretty spectacular. If I go into hydrogen with a fuel cell, and that is for an aircraft or a car, because this is my system before integration, I will lose a significant amount in the water electrolysis. I will lose some more in the transport, storage, and distribution, assuming you remain local. I mean, importing hydrogen on long distance is a total nonsense. Okay, so your hydrogen is produced and you use it locally. It doesn't cope with international shipping. So you are already at 59%. And then you go from tank to wake and you lose another 50% because of the fuel cell, and you still lose with the electric motors another 4%. So your overall yield is 28%. If I rephrase it, between a hydrogen car and an electric car with battery, you need 3 more times electricity. Okay? I do not know any single country who can afford to build a system which is 300% less efficient than another one. It really doesn't make sense, but I will come back on that on my conclusions. And then, because you will see after I have issues with gravity when I try to fly, if I pick the hydrogen and place it in a turbine, but then I have the very low efficiency of the combustion, so 27%. So my yield is 16%. And if I go on an e-fuel, so basically with a Fischer-Tropsch process, carbon CO2 capture, carbon, it's usage, it's not S, I made a mistake here. And then the Fischer-Tropsch, we know how to combine hydrogen and CO2 and to make a liquid fuel out of that. You can see that my yield is still very low, 15%, but interestingly, it is very, very close to pure hydrogen. Okay, and I will come back on that for aerospace usage. But there, basically, what it says is that I need 5 times more electricity than if I can be fully electrified. Those figures for road transportation are fully valid. Okay, so your electric car based on electricity, when you have a company telling you, I want technological neutrality and e-fuel can be efficient tomorrow, no. You have 500% difference between the two energy carriers, electricity and e-fuels. So those figures are before the integration, and the integration, when we compare cars or trucks and helicopters and planes, are very, very, very different. So also as an engineer, you need to understand basically the well to tank and all the energy return on energy invested principles. And then when you go from tank to well or tank to rotor or tank to motor, you need to understand the system you are working with as an engineer. In our case here, aerodynamics, weight and balance, thermal management are the key points. If I take MLW or MTOW, so basically the maximum landing weight and the maximum takeoff weight, you can understand that it is very different when you deal with kerosene and when you deal with hydrogen. And this is why I am very skeptical with the hydrogen plane, just because of that. There are many, many, many other reasons, but just because of that. I mean, when we design a plane, we need to take off. And so we will design the thrust and the energy we need to embed based on the maximum takeoff, understanding that the maximum takeoff is very different from the mass landing weight. Basically, a plane it carries passenger, but first it carries fuel. You have more fuels in weight than passengers in every plane. When a plane lands, we consider that the fuel tanks are empty, and the plane is much, much, much lighter than when it lands than when it takes off. Remember, if you take the jumbo jet, the Airbus A380, you have 320 tons of fuel. Okay, 320 tons of fuel when it takes off. When we land, we basically are around 20-25 tons. And so that 300 tons difference makes a lot of difference in the structure of the plane, in the landing gear design, in the belly fairing design, and so on. When you have hydrogen weight is nothing, but the hydrogen tanks weight is huge. And that weight of the tanks is not disappearing during the flight. So this is a single reason amongst dozens of other reasons that when we consider hydrogen in a plane, it's very, very difficult to make a design which makes sense, basically. So we have a plane. It can be a VTOL, so vertical takeoff and landing. It can be a conventional takeoff and landing, so a plane, or a short takeoff and landing, which is a kind of plane, I would say. And so we have a very versatile machine. And so it makes comparing apple to apple very complicated. Typically, this is for the helicopter, because this is where I spend my PhD in designing and testing. And so when you have a helicopter, the same helicopter can do medevac, can do offshore transportation, can do firefighting, military, and others. So basically, you use it for missions which goes from 20 minutes to 3 hours, and for distance which goes from 5-10 kilometers if you do utility, to 300-500 kilometers if you do, for example, a transportation of a patient or a military operation, or offshore. Typically, generally, you fly 200-300 kilometers to the platform and then way back. So the versatility makes it complicated. So the decision in the figures I will present, the idea to compare the different propulsive architectures and the different energy carriers which are at stake was to introduce a mission profile. And the choice of a mission profile was complicated because we cannot take, in fact, the initial design of a helicopter to compare, because if not, it immediately disqualify battery electrification in our case. And we wanted to introduce battery electrification so that we can compare the different energy carriers and the different propulsive system. So we pick what is the maximum, really the maximum of direct electrification, so which is a 45 minutes mission with a very limited payload of 4 passengers or 400 kilograms of payload on board. So it is a narrow application, but with such application we can compare everything, and we can compare apple to apple. So when we have that, we do our design. Basically, in our world, the design are based on the Freud ranking theory, and then we go on a statistical design method, so that we can make sure that we can basically lift, we can hover, and we can do the distance with the payload we want to carry. And so we apply that statistical design method over and over, using the different hypotheses for the components we have. So because this is the weight, this is the empty weight of our machine there. And there I put in red that we have been very optimistic for the batteries. You can see we choose a cell of 600 watt-hour per kilograms, which does not exist today, and which most probably will not exist in the coming decade. But as I mentioned, we did not want to disqualify full electric for that study. We also went to a depth of discharge of 90% and also an end-of-life energy of 85%. So we have been very, very optimistic hypothesis for the electrification, okay, on purpose. And so we apply our statistical design. We have the mission profile, and so we check with the mass takeoff weight assumptions. We do the sizing of the helicopter with the energy on board and the propulsive system weight. We do the power profile required at the rotor, And then we go on the propulsion system sizing and energy we need to embark on board. And do we have a takeoff or no? If we have the mass takeoff weight, which is below our assumption, it means we need to get a heavier helicopter with more energy on board, with more powerful engine, so that we can fulfill the missions. And we do that loop again and again until our assumption is validated, and then it gives the energy consumption for the mission. When we do so, here you have the main results. You have the weight of the main components, so the weight of the fuel cell and the H2 tank, the weight of the thermal engine, if we apply it, the weight of the electric motors, and so on. And then in blue here on the right, you have the main results. So you have the propulsion system weight. You can see there is a huge difference between battery and hydrogen system based on conventional fuels and therefore on e-fuel, which is my last line here. That means that the helicopter takeoff weight is very different. In our baseline scenario, it is a 1.4 tons VTOL helicopter. If we go into a full electric, it's more than doubled. We are close to 3,000 kilograms for the machine. And then you have the quantities of energy we need to spend to do the mission and on board. So for electricity, it is kilowatt hour of electricity. For hydrogen, it is kilograms of cryogenic hydrogen. We need liquid hydrogen. If we are gaseous, it's too big and we have too much drag. So we need to be cryogenic. And then you have the weight of the e-fuel. Remember, I mentioned we have 12 kilowatt hour of energy density per kilogram of e-fuel. We have 33 per kilogram of hydrogen. You can see that there is already here a factor 3 between the two. So when we have that result, then we can look, if we want to look at the impact, I would say it's at the end of the systemic approach before going back to a holistic approach. What is the total electricity consumption for my missions? Let's say I can afford to have a 2,900 kilograms helicopter. What is the quantities of electricity I put on board? And if I choose the e-fuel, you can see 1,575 kilowatt hour of electricity to do the mission. It's even more if it's hydrogen, either if I put the hydrogen in a turbine, if I burn it in a turbine, or if I place it in a fuel cell. And it is only 400 kilowatt hour of electricity if I choose the battery electrification. But remember that in our case, and I come back here, when I am with hydrogen, but especially with battery electrification, I cannot do much more than the mission we have chosen. So I totally lose the versatility of the machines. And remember also the assumptions of 600 watt-hour kilogram, the battery cell density. So the battery electrification, it's difficult for takeoff, and I have a lot of limitations. And when I go from e-fuel to hydrogen, my electricity consumption is roughly 50 to 70% more. So the basic conclusion at that stage is, why bother with a hydrogen system? If I have hydrogen, I rather transform it on ground to an e-fuel, basically, than taking I would say, overweight, and not mentioning all the safety issues and storage issues, boil-off issues, and so on, if I have to deal with that molecule. So when we are here, I can, since I have the electricity consumption, the assumption is that I can take that electricity from the grid, and then it's very easy to compare the different architectures with the energy carrier being electricity, and my CO2 emissions, they are directly proportional to the electricity carbon intensity multiplied by the electricity required for the missions. Here's a graph we made in the publication. It was with maximum of 340 grams of CO2 per kilowatt hour. Today in India, you have a lot of coal, so you are way above that number. Based on the question I heard during the panel, it doesn't change the interest of direct electrification for cars. But if you want to put electricity in hydrogen or e-fuel, it changes everything. Because we need a lot of electricity, we have a very low energy return on energy invested. And basically, keep that number in mind. you have no low carbon hydrogen or no low carbon e-fuel as long as you have more than 7% of electricity generation issued from fossil fuels. I mean, the carbon footprint will be too high, and basically you'd rather use fossil oil than an e-fuel or hydrogen in those cases. Totally different for direct electrification for batteries for cars. But if people tell you work on hydrogen or work on e-fuel, this is fully valid figures. Time is running, so I will go on that. And also to understand the cost is very easy. The cost is the same as for the CO2 emissions. The cost is directly proportional to the electricity cost multiplied by the electricity requirement for the emissions you're having. And with that, I can move on to the holistic and to the conclusion again. So the future cost of the mission, when we move on those energy carriers based on electricity, it is impacted by the cost of the primary energy, in that case electricity, multiplied by the energy return on energy invested we have chosen for the molecules we want to transform, multiplied by the system efficiency. So that means that technological neutrality, we hear that a lot in Europe. I hope you don't hear that too much in India. But technological neutrality doesn't make sense at all. It's pure marketing. You must assess the efficiency and the energy return on energy invested to compare the different systems, because you've seen that you can have a 500% difference in efficiency, and I do not see a system which can afford to be 500% less efficient than another one. And then comes the issues on the impact, the volumes of electricity you will take to the system, knowing that you have other users. So you are increasing competitions, and in an open market, increased competitions, if the demand is higher than the offer, the prices are going up. And electricity serves vital needs. I mean, we need to clean water, we need to bring water with electric pumps, we need to heat, we need to cool our food, people during heat waves and so on. So electricity is a vital need for many people, for everybody in fact. So if you have a very inefficient system which requires five times more electricity than another one, you are going into troubles. You also can compare the cost of the different solutions, and you can see that for aerospace, going into sustainable aviation fuels, coming from the most efficient biomass, is already very expensive compared to fossil fuels. And going into e-fuels, the price will be very different countries to countries, because the price of electricity is very different countries to countries. But you can see that in every case, it is much more expensive than the good oil fossil fuels that we need to get rid of. I'm not defending fossil fuels. I mean, we need to transition as fast as we can, but that comes with efficient systems, and that comes with a cost for societies that we must understand and acknowledge. Another issue which comes with the electricity policies is the energy justice. These are figures I've built for France. It's an important article I published earlier this year in Climate Policy. But you have the same principles in India. I mean, you have your energy, and then you have taxes on that energy. The difficulty with hydrogen and e-fuels is that we require a lot of electricity. And the taxes are very different. Here you have the taxes in France on the household, you have the taxes for the industries, and you have the taxes for e-fuels and hydrogen. And you can see that the taxes are very lower for the e-fuel and for the hydrogen. This raises significant energy justice concerns. And in 2 slides, I'm over. The first one is that you've noticed that if I want to do e-fuel, and in a plane, it is the most efficient or the least inefficient molecules I can use compared to electricity or to hydrogen. I mean, e-fuel is, I would say, the best, but clearly best. If I want to go from Paris to New York, and that works from Delhi to Paris, basically, this is the quantity of electricity I would require, kilowatt hour, and then I compare it with electricity you use in your everyday life, for heating, for cooling, for hot water, for lighting, and so on, and also the electricity you use for your electric cars, assuming you do 10,000, 12,000 kilometers a year, which is basically what we do in France. as an average. And you can see that the amount of electricity is huge just for a single trip. Okay, so this means within the populations there will be significant disparities. And this is my last slide. I will say on that. When we take the taxes associated, here you have the volume of electricity, and here you have the taxes. And basically, the electricity everybody used for hot water, lighting, cooling, basically for all the vital needs, is heavily taxed. Electricity for the local mobility, such as an electric cars, is heavily taxed. But the electricity for e-fuel for planes is almost non-taxed. So there will be disparities between the population because the tertiary needs basically is not taxed when all the vital needs are fully taxed. And so these are the kind of questions which comes when you design a system based on different kind of energy carriers. So be wise, be clever in the choices you do, and look at efficiency and equity, I would say, as often as possible. Thank you very much for your attention.
Long live India and France friendship.